Hello everyone. Welcome to the course Basics of Materials Engineering, and in week 6 we'll be talking about failure of materials. So in this we'll be basically talking about fracture mechanics. So this course is offered by Professor Ratna Kumar from Department of Materials Mechanical Engineering, IIT Madras, and I am your TA Alka Jangid from IIT Kanpur. Now, firstly, we'll be going through some sample assignment questions which will be helping you in solving your assignments, and then we'll be going through some lecture notes. So, first question is, brittle fracture is more dangerous than ductile fracture because. Now, what are the reasons for that brittle fracture is more dangerous? So, your options are no warning sign, crack propagates at very high speeds, or no need for extra stress during crack propagation, or all of the reasons. So your answer will be all. Now in case of brittle fracture, what happens that there is no plastic deformation or very low plastic deformation, which leads to very fast crack initiation and propagation at very faster rates without requiring any higher stress, and this leads to no warning signs before the fracture of material. So these all are the reasons for brittle fracture to be more dangerous. Now second question is, fracture toughness KIC decreases with, your options are increasing temperature, increasing strain rate, increase in yield strength, or increase in grain size. So fracture toughness answer will be increasing strain rate. So these are various parameters which affects fracture toughness. So if we increase the strain rate of loading, then it leads to decrease in fracture toughness. So this will be your answer. And in case of specimen thickness, if we increase this, then also fracture toughness will decrease. And if we decrease the temperature, then fracture toughness will also decrease. And this is the trend for the fracture toughness with strain rate. So as we keep on increasing the strain rate, your fracture toughness comes down in impact area. So in slow loading, there will be higher fracture toughness compared to high strain rate. Now question third is, for an even material experiencing plane stress loading, the maximum normal stress theory provides a reasonably accurate prediction for failure of brittle materials when both the principal stresses have the same sign. Your options are true and false. Answer will be true. So this can be explained as I told in previous lecture. So in case of brittle material failure, they are predicted by principal stress theory. So this will be true. Question 4 is, a rod with a circular cross section is subjected to pure torsion about its longitudinal axis until failure. The rod failed at the center along the length, and the failure surface is at an angle of 45 degree to the axis. We have to identify the most appropriate sentences. So your options are, the rod is made of a ductile material, rod is made of a brittle material, failure is limited by normal strength of material, or it is limited by shear strength of material. So two of the middle sentences are correct. Now we can explain this particular sentence by saying that when a solid rod is subjected to a pure torsion, then pure tension torsion will be the case of pure shear, in which principal normal stresses occur at 45 degree angle to the axis, and the maximum and minimal principal stresses are equal in magnitude and in opposite the direction. Now brittle material is weaker in tension, so brittle material shaft under pure tension feels along a plane at an angle 45 degree to the axis of the shaft, because the maximum tensile stress plane will be at an angle of 45 degree to the cross section of the shaft. Now in question 5, suppose that a wing component of an aircraft is fabricated from an aluminium alloy that has a plane strain fracture toughness 25 MPa square root of meter. It has been determined that fracture results at a stress of 112 MPa when the maximum internal crack length is 8.6 mm. Now for this same component and alloy, the stress level at which fracture occurs for a critical internal crack length of 6 mm. So you have different crack length, and corresponding to that you have to find out fracture stress. Now you know the formula for fracture toughness. So KIC equal to Y sigma root pi A. In this case, Y is your geometric constant, sigma is your stress applied, A is your critical internal crack length. Now crack length is given, your fracture stress initial is given, final you have to calculate. Now you can simply divide this formula with itself by taking K2, Y2, sigma 2 and A2, or you can get the value of Y root pi.
Ma'am, in this question,
Yeah.
like 8.6 is the internal crack length, no? So it is 2C. So our C will be 4.3.
Okay, internal crack length. So internal crack length is 8.6, then it is measuring 2C, right? It won't be giving
Yes,
you
ma'am.
half
So
of the length.
yeah, ma'am, it's measuring 2C. So in this formula, we should be taking 8.6 divided by 2, no?
So then both of will be 6 by 2 and 8 by 2. The answer will be remaining same in that case as well.
Oh, okay. Yes, ma'am. Yes,
Okay. So if it is on surface, then it is half or something like that. And so here you'll be measuring KIC. You don't need to give the value because it will be in both of the cases. Here it will be KIC and divided by KIC. So you can calculate using 112 root 8.6 divided by root 6. So it will be 134.09 MPa. Now this is similar question. Here you have to measure crack length. So yeah,
Sorry to interrupt, ma'am.
yeah.
Ma'am, like, can you just go through the first four questions? I will just take a screenshot, ma'am. Like, I'll
Okay,
later
okay.
revise it.
Okay.
Yeah. Yes, ma'am.
Done?
Yeah, yes, ma'am. Yes, ma'am. Ma'am, question number three did not had any explanation.
Yeah, it's just I told in previous lecture that most of your brittle materials are predicted using principal stress theory. So just true, it's true.
Yeah. Okay, ma'am.
Done? 3 done?
Ma'am, yes, ma'am. Three, four done. Yes, ma'am.
Okay. Fifth you joined, and sixth is similar. In sixth you have to measure critical crack length at stress level 75. So here similarly you are given, you are not given fracture toughness, but the material is same. So KIC will get cancelled when you will be putting in the formula. So 109, here you have to get value of A. So KIC square upon pi y square. So you can get the value of this y root pi using this, and you can get the value 11.82 mm. Now you can check this as well, because if you made some mistake in calculating, then you using the theory, like you can take that if you are increasing your stress, then your crack length should go down, required critical crack length, because it will be inversely proportional in root. Now question 7 is fracture voids usually form at. Your options are inclusions, second phase particles, grain boundary triple points, and or all. So answer will be all. Now in this case what happens, that it will give you an effect of type of delamination type of effect, which is seen in case of composites. So when fracture voids usually form at the interface of matrix metal and inclusion or second phase particle, because of different deformation rates in both of these materials, because both will have different strength, which will lead to formation of cracks at the interfaces. Now, eighth question is fracture stress sigma f is proportional to your crack length 1 upon crack length, or root square root crack length, or 1 upon square root crack length. Your answer will be this one, and using the formula you can simply measure this. Sigma will be your stress, so fracture toughness will be same for material. Then using this you have to get the relation between this sigma f and a. So sigma 1 and a1 and sigma 2 and a2, you can get this relation. So sigma will be proportional to 1 upon root crack length. Question 9. Now if the surface crack causing fracture in a brittle material is made twice as deep, the fracture strength will decrease by a factor of root 2, decrease by a factor of 2, or decrease by a factor of 2 square, or no change. Now we are keeping the fracture toughness same, and we are changing just crack length, and we are measuring what will be the effect on fracture strength. So similarly to your previous question, it will be 1 upon crack length. So initially it was a, now it is 2a, so it will be 1 upon root 2. So it will decrease by a factor of root 2. Now question 10. In a fracture mode 2, fracture surfaces shear parallel to edge of crack.
Ma'am, can you go to the previous one? I could not take the screenshot.
Okay.
Yeah. Yes. Yeah, sure.
Done?
Yeah, yes, ma'am. Yes, ma'am.
Okay, so in this question, okay, so in fracture mode 2, fracture surfaces shear parallel to edge of crack, shear perpendicular to edge of crack, or displace normal to each other, or none. Now you are given 3 fracture modes, right? So in first one it is opening mode. In this case your tensile type of loading will be there corresponding to your crack. And in second one there will be sliding mode, third is tearing mode. So in this case your shear will be in plane, in this one it will be out of plane. Now these are the relations with the this your edge of crack. So firstly in opening mode a tensile stress normal to your plane of crack will be applied, and in mode 2 your sliding mode a shear stress acting parallel to the plane of crack. So this is your plane, so it will be acting parallel to the plane and perpendicular to the crack front. In mode 3 it will be your tearing mode, and a shear stress acting parallel to the plane of the crack and parallel to the crack front. Now we'll be going through some lecture notes. So firstly, why there is importance of fracture mechanics. So when we initially started using some metals for manufacturing rails and your trains, your boats, there were a lot of accidents taking place. So increased use of metals in 19th century resulted in increased accidents and casualties. So, approximately 200 people per year were killed in train accidents in Britain during 1860 to 1870. Now, mostly were due to derailment of wheels caused by fractures. Now, these are various accidents that took place in Britain and in Liberty ship failures. Now, these also caused some casualties and a lot of economic loss. Now, these are the reasons we need to study fracture mechanics. Now, this is the aeroplane, and in this case, this commercial aircraft experienced an explosive decompression and structural failure on April 28, 1988, and investigation showed that the cause was metal fatigue, which was aggravated by crevice corrosion because of the change in environment, and an oil tanker that fractured in brittle manner as a result of propagation of crack all through its length. Now, several cracks may be observed during periodic inspections of commercial aircrafts. Crack or crack-like defects are found in ship structures, bridges, pressure valves, oil, gas pipelines, heavy machinery, vehicles, and other machine components. And cracks or crack-like defects are the primary concern in design of nuclear reactors. Now the pre-existing crack, they grow with the application of load, and crack length increases with time. Now the initially when we studied about ultimate tensile strength and yield strength, those all are calculated and those all are predicted by assuming that material is crack and defects free. So when we assume that it already has a crack, then the remaining strength of material in presence of crack is called residual strength, which reduces with an increase in crack size. Now, due to the presence of crack, residual strength reduces, hence the part is prone to failure from the expected high service load. Now, theoretical stress concentration factor, this is a factor which indicates the average load required for the onset of plastic deformation. And the KT is limited to structures with known dimensions, and it approaches infinity when there is a crack flow inclusion where the root of radius tends to 0. And the failure criteria studied so far can't be applied if there are flows or cracks present in the material. So all the theories that we studied, failure criteria, that considered that the material was flawless. Now yield strength, ultimate strength and buckling load based design can't be used. Hence a fracture mechanics based design is essential for the safety of components and structures. In this class will be mainly focusing on brittle type of fracture, and which involves only linear elastic fields around the crack tip. So there won't be any plastic deformation taking place here in brittle materials. Now these are three modes of fracture: opening mode, sliding mode and tearing mode. So based on these, your material can fail in different type of manner. It can fail in brittle manner or ductile manner. Now Griffith's experiment. So Griffith provided some experiment in which he took a plate and he took a crack using knife, and he kept on increasing the size of this crack. So he took a sheet and applied a force, then and holding in it grips. Now he used a knife to cut a slit normal to the loading direction. So loading is in this direction and your this direction of crack is in this direction. Now as he continued to increase the length of the slit with the knife, at a certain length without further help of the knife, the crack extends. Now the questions are, what is the critical length at which the crack advances on its own? So there will be a critical length that we used in the formula of fracture toughness. And can this critical length be changed for a given material? So as the material has different type of fracture toughness, it will be different for different materials. If a material is more tough, then it will require higher crack length to advance on its own. Now what happens if we alter the force applied to begin with? So if we apply more force, then the crack propagation will accelerate. Now Griffith's experiment, so he said that like surface tension in liquids, solids are also possess surface energy. So in a solid, all the atoms in bulk are surrounded by similar environment. However, for the atoms on the free surface and a few layers below the free surface, there is only bonding force from beneath and nothing on or very little from above. As a result, the surface layer of atoms experience strain, and the deformation of the surface atoms requires some energy called surface energy. Now, Griffith hypothesized that the crack in material advances when the released energy exceeds the energy required to create two new surfaces. Now, crack formation and energy balance. So, with an advancing crack, strain energy in the component decreases or increases, and stiffness of the component decreases because the thickness is reducing for material as crack is increasing. Now, the points of application of load may or may not move. Now, work is done on the component by the forces if the point moves, and the energy is consumed to create two new surfaces. Now we can say that the loss of the elastic strain energy will be equal to increase in surface energy when a crack is propagating. Now elastic strain energy is given by this formula, pi c square. C is your crack length, sigma is your stress, E is your elastic modulus. Surface energy of a crack, at the crack there will be two surfaces, so it will be 4c. C is your crack length again, gamma is your surface energy per unit area. Now you will be equating these two with by differentiating with crack length. So as the crack length is increasing, with that how this energy is increasing. Now both of these should be equal for crack to propagate. Now we'll be equating these two and we'll be getting this relation between sigma and this elastic modulus of material, surface energy of a material, and crack length. It will be sigma equals to 2 E gamma upon pi c whole square root. Now simple fracture. In case of fracture can be defined by saying that it is separation of a body into two or more pieces in response to an imposed stress that is static. When we are studying fracture mechanics, then we are assuming that this stress is static or very slow compared to what we see in case of fatigue loading, and at temperatures that are low relative to the melting temperatures, so that to separate it from the creep type of deformation. Fracture can also occur from fatigue and creep. So in case of fatigue, what will happen? There will be cyclic type of stresses. This will be studying in next chapter. And creep will be when there will be time dependent deformation at elevated temperatures. Now although applied stresses may be tensile, compressive, shear or torsional or combination of these, the present discussion will be confined to fractures that result from uniaxial tensile loading. For metals, two fracture modes are possible. They can be either ductile or brittle. Now this classification is based on the ability of a material to experience plastic deformation. Ductile metals typically exhibit substantial plastic deformation with high energy absorption, before fracture, which is your toughness of material. On the other hand, there is normally little or no plastic deformation with low energy absorption accompanying a brittle material. Now, in previous second chapter, we established a relation between your maximum stress required, theoretical stress required to deform a material to start slip. Now, shear stress required to slip by gliding plane of atoms in a theoretical shear strength calculated earlier. Okay, screen
Ma'am, did
share.
your screen is not visible?
Yeah, screen share stopped. Yeah, now it's visible, right?
Yeah, yes, ma'am, yes, ma'am.
Okay. Now, in this case, we assume that all the bonds are perfect and there is no defects present, such as dislocations or cracks present. So, the residual strength that we'll be talking, that is when there are some defects present, there are some cracks already present in the material. Now, the measured fracture strength for most materials are significantly lower than those predicted by theoretical calculations based on atomic bonding energies. This discrepancy is explained by the presence of microscopic flaws or cracks that always exist under normal conditions at the surface and within the interior of body of material. These flaws are detriment to the fracture strength because an applied stress may be amplified or concentrated at the tip. The magnitude of this amplification depending on the crack orientation and geometry. Now, these things that are reducing the strength of material, they are called stress razors. So, as indicated by this profile, here the magnitude of this localized stress diminishes with distance away from the crack tip. This is the profile. Now, this is the crack that's here. Around crack, the stress is very high. Your maximum stress is here. Now, as we are moving further to the crack, your nominal stress is sigma naught. It is keep on decreasing. Now, the sigma m upon sigma naught is your stress concentration factor, and this depends on the geometry of your crack and your size of the crack. And at positions far removed, the stress is just the nominal stress sigma naught or the applied load divided by specimen cross sectional area. Because of their ability to amplify applied stress in their locale, these flaws are sometimes called stress razors. And if it is assumed that a crack is similar to an elliptical hole through a plate and is oriented perpendicular to the applied stress, the maximum stress M occurs at the crack tip. This is sigma M, which occurs at the crack tip and may be approximated by 2 sigma naught brackets A upon rho T times half. Now, rho is your curvature of this crack tip. Now, stress intensity factor Kt. This Kt is your stress intensity factor. Now, for a system with different geometry and A being sufficiently small, KIC can be given as pi sigma root pi A. A being your crack length, sigma is your applied stress, y is your geometric constant.
Ma'am, one doubt I have in previous slide, like
Yeah.
in formula for calculating stress concentration, we use
Mm-hmm.
this radius of curvature at the crack tip. So, like, ma'am, like, which device is actually used to measure this radius of curvature at the crack tip?
Radius, okay, radius you can give 1 upon r is your curvature, right?
Yes, ma'am.
Formula of curvature will be, so radius you can measure depending on, okay, what device you'll be using. Okay, so in case of when you take materials and measure how the extension is there, you use DIC cameras. So using a picture as well, I think using you can measure these radius.
Okay, okay, ma'am. Okay, ma'am.
Like for wettability test as well, you measure what is the angle. So using camera pictures, you using pictures, high quality pictures, you measure what is the angle. So using those softwares as well, you can measure radius as well. But in your fracture strength, fracture toughness formula, there isn't radius. So here you just have to give what is the crack length. So, okay, moving further in static fracture mechanics. Now, fracture mechanics is a methodology that is used to predict and diagnose the failure of a part with an existing crack or flow. Now, here we'll be assuming there is already crack or flows are existing. Now, the presence of crack in a part magnifies the stress in the vicinity of the crack and may result in failure prior to the predicted using traditional strength of material methods. Now, the traditional approach to the design and analysis of a part is to use strength of materials concepts. In this case, the stresses due to applied loading are calculated. Failure is determined to occur once the applied stress exceeds the material strength, either yield strength or ultimate strength, depending on the criteria of failure. While in case of fracture mechanics, the stress intensity factor comes into play and it is calculated as a function of applied stress, crack size, and part geometry. The failure occurs once the stress intensity factor exceeds the material's fracture toughness. At this point, the crack will grow in a rapid and unstable manner until fracture. Now, fracture mechanics is important to consider for several important reasons. So, cracks and crack-like flows occur much more frequently than might be expected. Cracks can either pre-exist in a part or can develop due to high stress or fatigue. Now, typically, as the strength of material increases, fracture toughness decreases. So, for example, in case of ceramics, we consider them to be very low toughness materials. So, they will have low fracture toughness, but they have high UTS. The intuition of many engineers to prefer high strength materials can lead them down a dangerous path. Ignoring fact, yeah, Ignoring fracture mechanics can lead to failure of parts at loads below what is expected using a strength of material approach. A failure due to a brittle fracture is rapid and catastrophic and provides little warning. Now, this is the residual strength curve. So, residual strength curve shows the strength of part as a function of crack size. If no crack is present, the part strength is equal to the material yield strength. However, as the crack grows, the strength, the amount of stress that a material can withstand before failure is reduced. So this is given for particular geometric plate and for particular applied stress. So as we keep on increasing the crack length, the strength of material keeps on decreasing. Now, differentiation between ductile versus brittle fracture. Now, the brittle fracture mechanism is cleavage and the ductile fracture mechanism is dimpled rupture, also known as microvoid collapse, and the cleavage mechanism is associated with brittle fracture, which involves little plastic deformation, and the fracture surface looks smooth with ridges. The microvoid collapse mechanism is associated with ductile fracture. Now, in case of this brittle type of fracture, below crack there is only small region will be there where plastic deformation takes place. So this is known as linear elastic region. So only elastic type of deformation will be there near crack. In case of mixed mode fracture, there will be a bigger area where plastic deformation can take place. So there will be blunting of this crack. So there will be there will be higher time taken before this entire material fails. In case of ductile fracture, this material have high toughness, so these materials will show very high plasticity in crack tip. Now, any fracture processes involve two steps. Firstly, crack formation and propagation. Now, in response to an imposed stress, the mode of fracture is highly dependent on the mechanism of crack propagation, and the ductile fracture is characterized by the extensive plastic deformation in the vicinity of advancing crack. Furthermore, the process proceeds relatively slowly as the crack length is extended. Such a crack is often said to be stable and it resists any further extension unless there is an increase in applied stress. In addition, there will ordinarily be evidence of appreciable gross deformation at the fracture surfaces before failure. On the other hand, for brittle fractures, crack may spread extremely rapidly with very little accompanying plastic deformation. Such cracks may be said to be unstable, and the crack propagation once started will continue spontaneously without an increase in the magnitude of the applied stress. These are different type of fractures. So in this case, it is highly ductile fracture in which the specimen necks down to a point. Now these are the very ductile type of materials such as gold, silver, copper, these type of materials in annealed conditions. And B is your moderately ductile fracture after some necking. Now there is some necking occurring and then brittle fracture. Now in these cases, these are mild steel or these type of materials, aluminium type of materials, which will show this cup and cone type of fracture. C is your brittle type of fracture, which is mainly seen in ceramics or very high strength steels. These show no plastic deformation. Now ductile fracture is almost always preferred to brittle for two reasons. Now first is your brittle fracture occurs suddenly and catastrophically without any warning, and this is a consequence of the spontaneous and rapid crack propagation. On the other hand, for ductile fracture, the presence of plastic deformation gives a warning that failure is imminent, allowing preventive measures to be taken. So as this type of failure is occurring by taking some time, so we can remove that part, we can change that part before entire machine fails. Second is more strain energy is required to induce ductile fracture because these materials are generally tougher. So they'll be absorbing more energy before failure. Under the action of applied tensile stress, many metal alloys are ductile, whereas ceramics are typically brittle. And polymers, depending on what type of polymer is there, so they show range of behaviors. So they can be tough as well in in case of rubbers and all, and they can be very brittle as well in other cases, such as Teflon and other polymers. Now this is your mixed type of behavior, mainly ductile type of behavior, which shows cup and cone type of fracture. This is shown in aluminium type of specimens or mild steels. In this case, there will be initial necking. Necking is what? There will be reduction in cross section very abruptly when you'll be performing your tensile testing. So this reduction in cross section is seen, which is called necking. After that, here you'll be getting your UTS point, and then there'll be formation of cavities. Now these cavities are mainly known to form because of inclusions. So as I told earlier, inclusions will give your delamination type of effect. So these inclusions have higher strength compared to the matrix, so these will detach with the matrix, and these will make some voids, or there'll be vacancies will coalesce and form these type of microvoids. Now these will coalesce of the cavities to form a crack. This type of crack will form. Now this crack will propagate. Now final shear fracture at 45-degree angle relative to the tensile. Now this is will be your 45-degree angle at the tensile direction. So this is your fibrous type of and shear type of facets are seen here. Now there are two different type of fractures as well, transgranular and intergranular type of fracture. So these depend on the how they are fracturing along with the grain boundaries or from the grains. So in this case, in transgranular type of fracture, your crack propagation will be through the interior of grains, and this type of dimple type of structures will be seen below SEM. In case of intergranular fracture, this is seen when your grain boundaries will be very brittle in nature. So when these grain boundaries have some type of impurities present or hydrogen embrittlement, then your material will fail through grain boundaries when grain boundaries are weaker. So your crack propagation will be occurring along grain boundaries for intergranular fracture. Now this is your SEM micrograph showing intergranular type of fracture. Now this one I told earlier as well. So these are the stress concentration and notches in formation in some designs which we try to avoid in some materials. So a hole, a groove, a fillet, an abrupt change in cross section, it disrupts your force flow. This type of lines, so in this case your material is more likely to fail and initiate crack from these type of these edges. So these notches are of concern in machine components such as fastener holes, keyholes on shafts, o-ring grooves, etc. Now notches and stress concentration, these geometric stress concentration which is increase in stress at a local location due to change of geometry. Now sigma max equal to kT upon sigma nominal. This I told earlier as well. This is your stress concentration factor. So it is also an function of your geometry of your crack. So in case we have considered it ellipse, so its half length is A and its half height is C. So in terms of this as well, you can write your stress concentration factor. So with increase in C upon A also you can see how stress concentration will change. Now, one of the question in your assignment is based on this type of geometry as well, where you are applying a tensile type of loading or torsion type of loading. And based on that, you have to just get the values of R upon D and D upon D. Based on that, you need to find what is the stress concentration factor. Then using sigma max and sigma nominal, by calculating these things, you can find out what will be your failure strength. Okay, so that's all from my side. If you have any query, you can ask. So I can repeat the questions. So first question was, what is the brittle fracture is more dangerous than ductile fracture? Because no warning signs, crack propagates at very high speeds, no need for extra stress during crack propagation, or all. So your answer will be all, and you can explain this by saying that brittle fracture is more dangerous as material fractures without any warning, as very low plastic deformation occurs, which leads to very easy propagation of crack. Second question is, fracture toughness decreases with, your options are increasing temperature, increasing strain rate, increase in yield strength, increase in grain size. Answer will be increasing strain rate. Now, these are the various relations from fracture toughness and various parameters. So as we keep on increasing strain rate, your fracture toughness will reduce. As specimen thickness increases, your fracture toughness will reduce, and decreasing temperature will lead to decrease in fracture toughness. For an uneven material experiencing plane stress loading, the maximum normal stress theory provides a reasonably accurate prediction for failure of brittle materials when both the principal stresses have the same sign. Options are true or false. So answer will be true, and we can explain this by saying that brittle materials failure is predicted mainly by principal or normal stress theory. Fourth question is, a rod with a circular cross section is subjected to pure torsion about its longitudinal axis until failure, and the rod failed at the center along the length, and the failure surface is at an angle of 45 degree to the axis. Identify the most appropriate statements. The rod is made of a ductile material. Rod is made of a brittle material. Failure is limited by the normal strength of material, or failure is limited by the shear strength of the material. We can explain this by saying that when a solid rod is subjected to pure torsion, then pure torsion will be the case of pure shear, in which principal normal stresses occur 45 degree to the axis. The maximum and minimum principal stresses are equal in magnitude and opposite in direction. And the brittle material is weaker in tension, so brittle material shaft under pure torsion fails along a plane at an angle 45 degree to the axis of shaft, because the maximum tensile stress plane will be at an angle of 45 degree to the cross section of the shaft. Fifth question is, suppose that a wing component on an aircraft is fabricated from an aluminum alloy that has a plane strain fracture toughness 26 MPa square root meter, It has been determined that fracture results at a stress of 112 MPa when the maximum internal crack length is 8.6 mm. For this same component and alloy, the stress level at which fracture occurs for a critical internal crack length of 6 mm is blank MPa. Now we can explain this by taking the formula KIC equal to Y sigma root pi A. KIC is your fracture toughness, Y is your geometric constant, sigma is your stress, A is your critical internal crack length. Now putting all the values, you can find out the value of Y root pi, and then you can put in the formula and get the value of sigma 2. If fracture of aluminium occurs at a stress of 109 MPa, then the maximum internal crack length is 5.6 mm. For this same component and alloy, what will be the critical internal crack length at a stress level of 75 MPa? Using same formula as we used earlier, you can find out what will be the crack length. So A can be given as KIC square upon pi y square. Pi y square you can find out using this y root pi squared. Then you can find out the, okay, here sigma square will also be there. So using this you can find out the value of A. So it will be higher because we are reducing the stress level, so the crack length required for critical, it will be higher. Fracture voids usually form at inclusions, second phase particles, grain boundary triple points, or all. So your answer will be all. Fracture voids usually form at interface of matrix metal and inclusion, second phase particles, because of difference in deformation rates in both these materials, leading to formation of cracks at the interface. This again, fracture stress is proportional to fracture stress is your sigma F here. So using this you can find out sigma will be proportional to 1 upon root crack length. In ninth question, if the surface crack causing fracture in a brittle material is made twice as deep, the fracture strength will, your options are decrease by a factor of root 2, decrease by a factor of 2, decrease by a factor of 2 squares, or no change. So here you have to just use previous formula, and sigma equals to 1 upon root crack length. So initially it is A, then it is 2A, so it will be 1 upon root 2, so it will be decreasing by a factor of root 2. 10th question is, in fracture mode 2, your fracture surfaces, your options are shear parallel to the edge of crack, shear perpendicular to the edge of crack, displaced normal to each other, or none. So these are various factors and these are various modes. So first mode is opening mode, in which tensile stress normal to the plane of the crack is applied. In mode 2, a shear stress acting parallel to the plane of the crack and perpendicular to the crack front is applied. In mode 3 is your tearing mode, in which a shear stress acting parallel to the plane of the crack and parallel to the crack front is applied. Now that's all.
Mm.